Welcome back to the tail end of the Gauss's Law lecture that we didn't have time to finish up last time. So, I mentioned before that Gauss's Law is this way that we can solve for electric fields without doing any calculus. All right? And that's the real strength of it. What it does is looks like this big, nasty, horrible, closed surface shape integral thing with the double squiggle and the circle through the middle and a dot product and a dot dA, and you don't even know what that means if you're in Calc BC. That's a multivariable thing. But the point is, it just represents an idea. This idea is just the total flux through the closed shape, just like we did through this for the cylinders. Okay, so once again, the left side is the total flux through like one of those cylinders that we did the examples for. The left side is the total flux through the closed shape. Okay, so the left side of the equation is the flux through a closed shape, through like one of those cylinders, top, bottom, and left, right sides, right? The right side says all that flux equals the charge enclosed divided by a constant. Well, that means all you have to do is figure out how much charge is enclosed by that cylinder, divide it by epsilon naught, and that equals the total flux, which is kind of cool. So we're going to actually use that for a sphere. We're going to say, and this is where it gets a little goofy, and we're going to have to practice this a little bit. We're going to say, let's say you had a charged particle right there at the center. And you know that charged particle creates, if it's a positive charge, it creates electric field that radiates out in all directions, right? I'm going to say, what if you drew a sphere around that charged particle? A perfect sphere where the particle was at the center of the sphere. All right? We're going to call that sphere a Gaussian sphere, or a Gaussian surface. All right? Now, if you notice, because that Gaussian sphere is concentric with the charged particle, all of these electric field lines hit and cross through the surface of the Gaussian sphere at a 90-degree angle. Right? They come in and cross through like that. What we can say is that the total flux through that sphere is equal to what?
Is equal to the charge over
Q divided by epsilon naught, right? The total flux through that sphere. But you guys know that the total flux is the field times the surface area of the sphere, yes?
Yeah.
So E times A of the sphere is the total flux equals Q over epsilon naught. Agree?
Yeah.
All right.
Sean's here.
All right. You know also the area of the sphere is, do you guys remember our equation? Area of the sphere? No, not pi r squared.
4 pi.
4 pi r squared for an area of a sphere, right? 4 pi r squared for a sphere. Also, you know the electric field at this radius is kq over r squared, right? Or 1 over 4 pi epsilon naught q over r squared. Now, let's try this. All right, so here's where it gets interesting. We know that the total flux is E dot dA, integral of E dot dA. But in this case, since E is constant at all those A's, we can just say E times A. Because there's, what's cosine of 90, by the way?
0.
Oh, sorry, not 90.
0. Cosine of 0.
Cosine is 0, right? Because E and dA are always pointing in the same direction. So the cosine goes away, it just becomes 1. So it's E times A is the flux. Well, E is how much? 1 over 4 pi epsilon naught times Q over R squared. So that's E. And then what's A of the circle?
The surface area of the sphere.
4 pi R squared. Guess what happens?
Cancels.
Everything cancels.
Except for Q.
4 pi's cancel, R squareds cancel, and you're left with Q over epsilon naught. So we know, therefore, that the flux through a sphere has to be Q over epsilon naught.
We won't need to derive that, right?
You just did.
I know, but we won't need to.
Oh, no, this is like the simplest possible example. Yes, you will be doing this problem many, many, many times. Yeah, this is like the bare bones basic versions of Gauss's law. All right? So the key is you figure out an electric field and you figure out an area of the shape. Multiply them together, and that equals the flux, right? And that equals Q over epsilon naught. All right, so here's the crazy thing about this. This doesn't just work. This flux equals Q over epsilon naught is not only true for a sphere, it's true for any closed shape. All right, I'm just showing you the derivation for a sphere. If you want to take multivariable, you can do it for a random arbitrary shape. All right, and you guys did that in multivariable, I think?
Yeah.
Yeah. All right, we don't care. All right. The way we're going to use Gauss's law, it's all just basic algebra. All right? So, that's it. Let's move on.